My name is Tom Walski from Bentley Systems, and welcome to our presentation on using the SewerGEMS model to predict hydrogen sulfide formation in wastewater collection systems. Before we get too far into the actual presentation, I just want to say a little bit about Bentley Systems. Bentley Systems, as you know, is the leading company for software for infrastructures. And while today we're going to be talking about wastewater collection systems, Bentley really has products across the whole gamut of infrastructure, including roads and architecture and bridges and railroads and offshore platforms. But today we're going to focus in on the area of wastewater collection systems. In particular, we are going to focus in on the SewerGEMS model, which is used for wastewater collection, design, and operation. You see we have a whole bunch of other products in the water and wastewater area, including the water distribution systems, mapping, stormwater systems, treatment plant design, asset management. So we have a lot of products along these lines. But today we're going to focus in on SewerGEMS for hydrogen sulfide modeling. Overview to talk. First, we're going to talk about just hydrogen sulfide in general and the issues that are involved in working with hydrogen sulfide. Looking at hydrogen sulfide chemistry, how does this stuff form and why is it such a problem? Then we're going to look at using the models to predict the formation of hydrogen sulfide in collection systems. And then we'll talk a little bit about managing hydrogen sulfide, what you could and really can't do about it. Hydrogen sulfide, as you know, is a problem. It has kind of a bad guy in wastewater collection systems. Things would be a lot easier in our lives if we didn't have to deal with this sort of thing. The chemical symbol for it is H2S, hydrogen sulfide. Sulfur has a valence of 2 in this particular case, although sulfur forms a lot of different kind of compounds. Why is it a problem? Well, it's a problem on a whole number of fronts. It's an odor problem. It corrodes things. And it's a safety problem because it's toxic even at fairly low levels. So when you're working in a sewer system, you really have to follow the confined space entry procedures, or else you can end up in a lot of trouble because of hydrogen sulfide. Okay, let's talk about the chemistry of sulfur. This is a chart of the sulfur cycle that I got from the ASCE manual on hydrogen sulfide formation and control, manual practice 69. We see, as I mentioned earlier, sulfur can form a lot of different compounds because it has a lot of different oxidation states. What we're looking at here in the diagram, though, is up at the top, hydrogen sulfide, which is usually formed by the breakdown of sulfate in the presence of anaerobic bacteria. So we need bacteria that can live without oxygen. They're looking around for oxygen, so they look at the sulfate ion, which has oxygen attached to it, so it pulls it off there, and again you just have the sulfur with a -1 valence at the end of this. And that's the guy that causes a lot of problems because sulfate isn't really a problem, and sulfate is very prevalent in wastewater. So you have a lot of sulfate there, and a lot of anaerobic bacteria that want to pull the oxygen off the sulfate. So it's a difficult situation. The overall chemical formula here is basically you have sulfate, and the bacteria that like to reduce sulfate to sulfide are pretty much everywhere in sewer systems, and they don't have any other source of oxygen because they've used up the elemental oxygen, they used up the oxygen they could pull off of nitrate molecules. So pretty much if they're looking for something to eat, basically, they look at the sulfate as a source of energy. And then the sulfate, of course, can exist in different oxidation states as well, whether it's at low pHs where it's generally as a hydrogen sulfide dissolved in the water, and it can form sulfide ions at higher pHs. So as I said, in general, at low pH, it's mostly hydrogen sulfide dissolved in water, and it turns into the ionic form at higher pHs. Hydrogen sulfide, though, is relatively insoluble in water, which means it wants to escape and get out into the gas phase. Problem with this is where it causes a lot of the problems. The gas, as I said, is toxic, it smells bad, and it reacts with things to corrode. So it's not a good thing to have hydrogen sulfide form. It forms when there's no oxygen present, well, which is the case in most sewer systems. You know, microbes use up the oxygen pretty quickly. There's plenty of food for them in the form of BOD and ammonia and these kind of things that they can consume. So oxygen is pretty much lacking in collection systems. And the microbes like to do is generally like to live on in the slime layer, either along the bottom of the sewer or in sediments along the bottom. And so there's no shortage of environment for the microbes that create hydrogen sulfide to exist in sewer systems. It's just a matter of what is the rate at which it forms, and can we get the wastewater down to the treatment plant before it causes a lot of problems due to hydrogen sulfide formation. So once the hydrogen sulfide forms in the liquid phase, and it likes to form in sewers that have a lot of solids deposited at the bottom, what you want to do is to prevent those from settling. So you want to design sewers, of course, to maintain adequate velocity, to have the right slope, provide the right tractive force, so you don't have as much of a slime layer forming as much as a sediment layer at the bottom, because that tends to make the problem even worse. But then the hydrogen sulfide wants to come out of solution. It releases out of solution at drops, at hydraulic jumps, at places where forced mains convert over into gravity mains, and this frees up the hydrogen sulfide to form the hydrogen sulfide gas that attacks concrete pipes, metal structures, anything that is corrodable, it will attack, and it will be noticed as an odor. Well, how bad is hydrogen sulfide? Well, at even very low concentrations, it's irritant. As it gets higher, it starts to cause headaches and dizziness once you're exposed to it for a while. Eventually, it results in loss of consciousness as the concentration climbs upward. And at a high enough level, a long enough exposure, can be fatal. Every once in a while, you'll hear a story of someone who died due to hydrogen sulfide exposure. And what's also often tragic is someone tries to rescue that person and they also die because they've been exposed to those high concentrations of hydrogen sulfide. It causes respiratory paralysis. It also affects the olfactory senses. So when you first enter an environment that has a lot of hydrogen sulfide, you say, oh, that smells terrible in here. And after a while, I don't smell anything. It's gone away. There's no smell left. So this can be really bad because then you don't realize that you're being exposed to a toxic environment. So what you have to do whenever you're working with sewer systems, especially in places where you expect hydrogen sulfide to be present, is follow the confined space entry procedures. Most of the illnesses and fatalities happen by people who don't follow confined space entry procedures. It's very dangerous. Always, when you're going into these environments, take along your gas detectors. And when they tell you the hydrogen sulfide concentration is too high, get out of the area. So what kind of levels are high? So we talked about levels that can cause danger. Well, what do the safety people recommend? Like OSHA and NIOSH, they have very low levels before they tell you you're in too high of an area. So they put in a decent safety factor so that you're alarmed and you're told to get out of an area or follow the correct confined space entry procedures at very low levels. And it doesn't take too much, though, before you get up into those IDLH levels, and immediately dangerous to life and health. And those are the cases where you really have to get out quickly. Don't stand around there trying to, well, I'll just hold my breath or something like that. Think in those terms. It's very dangerous, and you need to get out of the area where hydrogen sulfide is you're exposed to. Okay. Also, hydrogen sulfide, as I said, is corrosive. It corrodes all kinds of metals like iron, copper, steel, which happen to be things that are used in a lot of plumbing. Not a very good situation. Especially bad on concrete, because hydrogen sulfide gas exposes up to the top of the pipe, on the crown of the pipe, and the bacteria there, thiobacillus bacteria, cause it to form sulfuric acid. And you mix sulfuric acid onto concrete structures, and it turns it into calcium sulfate, which is known as gypsum, which is not nearly as strong as concrete. It's really, when gypsum is wet, of course, it becomes soft, mushy, and lacks any structural strength. And so pipes that were made of concrete, when you install them, that seem very strong, suddenly become little more than mush, and the pipe is gone. And you're wondering, why is this pipe corroded? Well, it's the hydrogen sulfide and the microbes along with it that cause this corrosion of your pipes. So let's look at some pictures here. Here's a stream crossing pipe on a force main that had to be replaced. This is the new pipe there because the old pipe at this high point is where gases would come out of solution and corrode the top of the pipe. So it had to be replaced with a new pipe that had better coatings on it to prevent the corrosion from reoccurring along this force main. This is a situation here that I was involved with personally of a concrete force main that the top was just corroded away. And we see the pipe being pulled out of the ground on the right side. On the left side, you see a temporary bypass that was put in while the new pipe that was lined with a plastic liner was installed at this high point. It was a high point along a force main. It wasn't a very steep high point, so there was no air release put in or anything. But instead, what happened was the pipe was eaten up by the hydrogen sulfide. It caused a lot of problems too, because when the force main was pumping, you would have sewage essentially erupting into the street. And as I said, it's not just concrete that's affected though. All kinds of metal things, including electrical equipment, can be damaged by hydrogen sulfide. And concrete pipes are still used. They're very good piping material. It's just that you need to be aware of where hydrogen sulfide is going to be bad and take the necessary measures to protect the pipe or prevent hydrogen sulfide from forming. And as I said, they're being installed even today. They're being used to replace existing pipes or the new piping systems. It's a good pipe material. Here's another place where the hydrogen sulfide can come out. This is pumping over a levee. And at the high spot of the levee, it's a great place where the hydrogen sulfide gas that formed along these force main will come out of solution and erode the pipe. And then, of course, when you pass by, it smells. And there are some kids that don't like the smell of hydrogen sulfide. It has what's called a rotten egg odor, although I usually don't try to go around smelling rotten eggs, but that's the kind of smell that you'll get from hydrogen sulfide gas. Here's another photo of a concrete structure at the end of a long force main. This is a force main that's several miles long, and at that concrete structure you see in the background, the pressurized force main turns into a gravity pipe. And whenever you pass there, you can smell the hydrogen sulfide any time of day, any time of the year. Hydrogen sulfide is evident in that area because it's built up along this force main. It had no place to go, and when it comes out of solution at the end of this force main, when it converts back to a gravity pipe, it comes right out of solution, and it's very evident at this location. So what about this chemistry? What rate does it form at? And how can we predict this formation? Well, the state of the art in this is the Pomeroy-Parkhurst equation. And it says that the rate of change of hydrogen sulfide or sulfide in the flow depends on really two terms. The first term is the rate at which it forms, and the second term is the rate at which it's lost to the atmosphere above the flow. So let's look at these individual terms. So the first term is the rate of change of sulfide concentration. It's going to depend on the BOD. How strong is the wastewater? What's the dynamics of the pipe? And M prime in this case, which is the sulfide flux coefficient. And I give a number there, a typical number in meters per hour, but really it's something you need to calibrate in for your system. What kind of values do you find and check them out. This will give you the rate at which the hydrogen sulfide is created, because you have plenty of sulfate in the flow, and the more BOD you have, the higher rate at which this is going to pull, the microbes are going to be able to pull oxygen off the sulfate and form sulfide. And you notice down below that it's also a function of temperature. At warmer temperatures, the formation reaction goes faster. That's why we have effective BOD with that E in front of it to account for the fact that the BOD is not, it's not just the BOD that determines things, but the temperature, because it's the rate at which the BOD is used up that's important. The second term is the rate at which the hydrogen sulfide goes off into the gas phase. Now, in this case, it's going to depend on how turbulent and fast the water's moving. So if you have a high slope and a high velocity, it's going to be stripped out faster and move up into the gas phase where it's going to be noticed. And N is a coefficient that kind of calibrates in your local system. But it's mostly this, the steepness of the pipe there, and the stripping of the pipe. It also depends how much hydrogen sulfide is present. If you have a lot of sulfide present, it's going to get stripped out faster. If there's none present, it's not going to get stripped out very fast. So that's why the S term appears also in the right side of the equation. Okay, once it's formed, we see the rate here. This is what we calculated in the previous equation, a rate of formation of hydrogen sulfide over time. It's going to depend on how long it's in that particular element, whether it's a pipe or a wet well, how long it's there. So it's whatever came in, the rate at which is new hydrogen sulfide is formed, and then what comes out. Now the the time at which it's available to have these reactions occur really depends on whether you're talking about a linear element like a sewer pipe or whether you're talking about a volumetric one like a wet well. So in a wet well, it's the volume divided by the flow rate through the wet well. In linear elements, it's the length divided by the velocity, how fast the flow is moving along that pipe. So how do we do this in SewerGEMS? What happens there? Well, SewerGEMS predicts the formation of sulfide, converting sulfate into sulfide based on the Pomeroy-Parkhurst equation that I showed you. And it works with our explicit solver. So in SewerGEMS, as you know, we have 4 different solvers available. So you want to choose the explicit solver when you're doing these particular calculations. And what we work on here is the average concentration, or basically the concentration based on average conditions, because hydrogen sulfide formation and corrosion is not a real dynamic thing. It's not like, you know, you put in some BOD and 15 minutes later you produced a great deal of hydrogen sulfide. It's really something that occurs over long periods of time. So you're really interested in the average concentration over the course of a day, not so much the little dynamic fluctuations that occur along the way. It's really what's the long-term exposure of people and facilities to hydrogen sulfide that you're really interested in. So we give you the average concentrations over the duration of that run. And the calculation doesn't take much time, so all the calculation time is used up in the hydraulic calculations. And once the hydraulic calculations are done, the extra time to make the hydrogen sulfide calculation is pretty much nothing. So it's not like there's a great computational burden from this. And while the Pomeroy-Parkhurst equation is set up for gravity pipes, we also have some minor modifications to work with force mains where you don't have any stripping of the hydrogen sulfide, and storage elements like wet wells where there's a slight different formulation needed. Okay, so how does this look inside the model? Okay, so we have to look at each element and how you enter data for each element. So in terms of conduit elements, the important thing is, first of all, the temperature, which affects the reaction rates, and then the flux coefficient, that M prime term. Usually, this is showing in feet per second. Usually it's given in meters per hour. It's like a 0.004 is what we use as a starting point as meters per hour. And then that loss term, the N term in the equation. So these are the inputs that the user has to provide for a conduit element. Now what you get out of the conduit element is the transformation, how much hydrogen sulfide went in and how much came out the other end. In this particular pipe, we had a very short detention time on average during the course of the day, so there wasn't really much of a change in hydrogen sulfide concentration. So there's only a slight increase along this particular pipe element. Another kind of element are the node elements, like manholes. In this particular case, you load in the BOD and hydrogen sulfide at the manhole. Now, there really isn't usually a lot of hydrogen sulfide in the wastewater that comes out of a typical house. There's not a lot of hydrogen sulfide. It hasn't had much time to form. So what really is being entered from the house is the BOD, which is the demand for oxygen. And it's going to be what drives the formation of hydrogen sulfide. So that's the BOD that is the driving force in that equation that you saw earlier. And what you get out of the manhole elements is the hydrogen sulfide out, the BOD out, and a detention time. This would be for a flooded manhole where you have some detention time. Most actual manholes have essentially a pretty negligible transit time through the manhole. Okay, force mains are similar, except that in force mains the loss factor should be 0 because there's no headspace at the top for the hydrogen sulfide to escape to. Now what happens here, you see, is you get more formation, and since the hydrogen sulfide in is bigger than the hydrogen sulfide out is bigger than what came in. There's a bigger difference because in this particular case too, there's also a longer detention time. So it's several minutes for the hydrogen sulfide to increase concentration. Wet wells are similar, but they have their own quirks in that the reaction rate is provided in a different set of units. Again, you have to do some testing to see just how hydrogen sulfide changes across a wet well. And usually there's no local inflows of BOD and hydrogen sulfide. Usually the BOD comes in at the manhole nodes, and there's no real source of hydrogen sulfide for the most part of anybody, producing it and dumping it into the system at the wet well or at any manhole node. But if you do have some source where hydrogen sulfide is formed, maybe some chemical process plant that is creating hydrogen sulfide, then you can actually enter that value at the node element. What you get out of here again is the hydrogen sulfide out, and it really depends on the detention time. If the wastewater sits in the wet well a long time, you're going to form a lot of hydrogen sulfide. So how do you tell SewerGEMS you want to do the calculation? Well, at first you pick the explicit solver, as I said. Then you go down to water quality, and where it says run hydrogen sulfide analysis, you change that false, which is the default, to true. And that tells it that run the hydrogen sulfide calculation in SewerGEMS. All right, so how do we look at the results? Well, a nice way to look at the results is, in this very simple case here, is just annotate or color code by hydrogen sulfide concentration. So we see hydrogen sulfide concentration starting off at 0, and it increases as it goes down, changes by quite a bit in the wet well. It goes through a force main where, again, it increases substantially. Then it turns back into a gravity pipe in this particular case, where it's actually starting to strip out some of the hydrogen sulfide because of the high velocity in that pipe. So this is a good way to look at the results, is with a color coding and annotation, which is available in SewerGEMS' element symbology. This looks at a more complicated system. Here we see fairly cool temperatures. We have some low reaction rates, and so the concentration doesn't get very high. But then as we turn in a very warm day with very warm wastewater, we see this hydrogen sulfide can form pretty dramatically. And by color coded by hydrogen sulfide, you can see where you're going to have the places that have a lot of hydrogen sulfide dissolved in the water. And for example, you take that same cool temperature and have a low aeration rate. We have very flat sewers. You're going to get less aeration. You're going to get more hydrogen sulfide forming. And as I said, color coding is a nice way to get that overall view. You could also look at the results, of course, in the flex tables for conduit or manhole elements. So what is the model going to tell you? What's it likely to tell you about hydrogen sulfide problems? Well, we have two columns here, and we see the good and the bad. The places where hydrogen sulfide is likely to exist are places that have warm water. So they're going to happen much more often in warm climates than in cool climates. It's going to happen in places where the wastewater is strong, because remember, the reactions are driven by the BOD available. So if you have a very strong wastewater, hydrogen sulfide is going to form faster. It's going to form more likely in pipes that have mild slopes, because with turbulence, you first of all keep a little bit of oxygen in the water for a little longer, and you don't strip out the hydrogen sulfide that's formed. So you're going to have higher concentrations in flatter pipes, plus flatter pipes are more likely to have solids at the bottom settling out, which are going to provide a better environment for these bacteria that form hydrogen sulfide. And you get more likely to have the problems existing in systems that are big, where the travel time from the far end of the system down to the treatment plant is a long distance. So, the worst case kind of places are places that have, flat slopes, long travel times, strong wastewater, and a warm climate. You put those things together, and you're going to have the worst hydrogen sulfide problems. Take a little small system with steep slopes up in the mountains where it's really cool, and you're not going to see nearly the hydrogen sulfide formation problem. So what do you do to control hydrogen sulfide? There really isn't too much you can do to control BOD or temperature. Those are pretty much givens. So there's not much you can do to control those, even though they're important things in that Parkhurst equation. You can, of course, during design, make sure you have adequate tractive force. Make sure the sewers have enough slope so that you don't have solids depositing in the bottom, and you don't have as much slime growth along the walls of the sewers. But once you have those conditions existing, then what you try to do usually is to use oxidation. If the problem is significant enough, or it's going to be a serious problem, oxidation of the hydrogen sulfide is the way to go. And there's a lot of chemicals that can be used to either prevent hydrogen sulfide from forming by getting oxygen into the sewer, or break down the hydrogen sulfide that forms. And there's a variety of chemicals. The problem here, of course, is these cost money. They're not inexpensive things to use for hydrogen sulfide control. Other things that people have done pH adjustment. They've dumped in a lot of caustic periodically to basically kill the microbes that like to live off the hydrogen sulfide. as another type of method. And the other case is if you're going to have hydrogen sulfide form, then protect the pipes. You see a lot more of inert materials used, or lined pipes or coated pipes, to prevent hydrogen sulfide from attacking the structural part of the pipe. Once it does form too, you have odor problems. So there's a number of methods for odor abatement. If you can prevent it from forming, great. If you can't, there are various kinds of sprays and things that can be used to knock down the odor of hydrogen sulfide or mask it in some cases, so that it's not nearly as bad of a problem. Because people that have to live alongside these facilities where hydrogen sulfide comes out are usually not really pleased with the odor that they're faced with. So how do we use our models in this case then? Well, you could use the model to find troublesome locations. Where is hydrogen sulfide going to form? You'll find, as I said, downstream of flat pipes that have a long travel time is generally the answer. So you can identify those troublesome loads and times of the year. Maybe during some time of the year, hydrogen sulfide is not a problem, but when you get into the warm weather of summer, you're going to have to do something, use chemicals treatment or so during those bad weather periods. Changing pump operation, if you can keep the time that the wastewater sits in the wet well down, then there's less chance of hydrogen sulfide forming in the wet well. So maybe speeding up pump operation or keeping the cycle shorter maybe. And so the hydrogen sulfide generation can be analyzed in models so that you can try things and see, what can we do to abate hydrogen sulfide problems.